Okay, let's unpack this. We're diving deep today into something that feels incredibly cutting edge, shaping our near future. But its origin story, it's actually quite surprising. It didn't start with startups and apps.
Not at all. The roots of artificial intelligence are, well, they're really dug into the necessities of a global conflict. World War II, basically.
And we're digging into that origin using a whole stack of sources you shared.
Yeah.
Our mission, really, is to find those key moments, the foundational ideas, the people who shaped AI right from the beginning.
Yeah, we'll trace it from, ancient myths about creating life, through the wartime pressures that made theory practical, to AI getting its actual name,
Right.
and then the first programs that could maybe think, and those big early debates that led up to the first AI winter.
So setting the scene,
Mm-hmm.
it's kind of wild that people have wanted to create artificial life for thousands of years. You see it in myths, right? Talos, the golem, then those amazing clockwork automaton.
They were incredible engineering feats, yeah. Really showing off human skill in mimicry. But the big shift came in the 20th century. The focus changed. It wasn't just mechanical copies anymore.
Right.
It became about the scientific possibility of machine intelligence. Not just making things look human, but making things that could, think, or at least do thinking-like tasks. Logic, math, early computing theory, they provided the tools.
And this conceptual jump gets a massive push from sheer necessity.
Absolutely. World War II. Suddenly you needed complex calculations, fast decisions, on a scale never seen before. Ballistics, code breaking, logistics. The computational load was immense. It forced these theoretical ideas about machines doing logic into, urgent practical problems.
There was also that cultural piece, wasn't there? The word robot coming into play.
Yeah, Karel Oppik's play RUR back in 1920. His robots weren't really machines, more like artificial biological beings, but still. It planted the idea of artificial humans in the public mind, maybe made later scientific talk about thinking machines seem a little less out there.
Okay, so necessity, a bit of cultural groundwork, and then this giant figure enters the picture, Alan Turing. His wartime role, even though secret for so long, seems absolutely key here.
Oh, completely central. Turing at Bletchley Park, the UK's code-breaking center. His work cracking the German Enigma codes, especially those tough naval ones, was just monumental.
And that involved bomb machine. We shouldn't think of it as modern AI, obviously, but what was its significance?
Right, the bomb wasn't thinking, but it was revolutionary. It was this electromechanical device that automated an incredibly complex logical process, testing Enigma settings super fast. The insight that tasks needing intense logic, pattern finding, systematic work, they could be mechanized. It showed machine power for complex problems against the clock, validating theory in a high-stakes situation. A huge, if secret, step.
So the war becomes this kind of unintentional proving ground for his earlier abstract ideas.
Exactly. Think back to 1936, years before the war. His universal Turing machine, purely theoretical then. An abstract model showing one machine could simulate any other computing machine, given the right instructions. That's basically the blueprint for digital computers.
And the key takeaway from that for AI.
It suggested that thinking itself, if you see it as a kind of computation, might be mechanizable. It introduced the whole concept of a program instructions separate from the hardware, absolutely fundamental.
So he had the theory, the practical proof from the war, and then after the war, he asked the question that kind of sets the course for the field.
The Turing Test. In his 1950 paper, Computing Machinery and Intelligence, he called it the imitation game. You have a judge, a human, a machine, text-only communication. Can the judge tell who's who? If not, Turing argued, the machine shows intelligent behavior.
What's so powerful about that? It feels simple, but also really deep.
Its genius was its pragmatism, really. It bypassed those endless philosophical arguments about what is thinking. Instead, it focused on behavior. Can it act intelligently in conversation? Maybe that's enough. It became the benchmark, though, instantly controversial.
And that controversy lives on, right? Does it just push AI to mimic humans, maybe missing other kinds of intelligence?
Exactly that critique. But even so, the test made people confront the possibility directly. And Turing himself was thinking way ahead. He talked about machines learning, changing their own instructions.
It's still pretty incredible that his crucial wartime work, the stuff that proved so much, was kept secret until the 1990s.
A huge loss for the early field, you have to think. He couldn't bring that direct experience into the public AI debates before he died.
Okay, so that's Turing in the UK. Meanwhile, across the pond, there's another related stream of thought building up with Norbert Wiener and cybernetics.
Right, Wiener, brilliant American mathematician. And like Turing, his war work was a catalyst. He worked on automatic anti-aircraft guns, trying to get machines to predict and hit moving targets. He saw the system needed to track, predict, fire, and then crucially adjust based on the result and the target's evasion.
That sounds like a feedback loop.
Exactly. And Wiener realized this wasn't just about guns, it was fundamental. Control and communication. He defined cybernetics as the science of control and communication in the animal and the machine. He saw this essential unity in how biological systems and machines handle these problems. Intelligence, control, life itself, all tied together by feedback.
So cybernetics gave people a way to think about intelligent systems even before the term artificial intelligence existed.
Absolutely. It focused on things like goal-directed behavior, self-regulation, processing data through feedback. It opened up this whole conceptual space for machines that could adapt, almost like living organisms. And those Macy conferences he was involved in were key, bringing together mathematicians, engineers, biologists, really mixing ideas.
And Wiener wasn't quiet about the implications, was he?
Not at all. He was a major early voice, but also one of the first to raise serious ethical flags. He worried about automation devaluing human mental work, leaving people with nothing to sell which anyone will buy, as he put it. He even backed away from military work later on because of it. His concerns about ethics were remarkably prescient. We're still wrestling with those same tensions.
He sounds like he became quite the public figure, almost a prophet of this new age.
He definitely was. And maybe that high profile, the sheer breadth of cybernetics covering everything from biology to society, maybe that created a need for something more focused, more technically defined. Which leads us right to the moment AI gets its name.
1956, the Dartmouth Workshop.
Yep, that's widely seen as the official founding moment for AI as its own field. John McCarthy, a young math professor at Dartmouth then, was getting frustrated. He saw the potential for computers to do really intelligent things, but felt the research wasn't focused enough. He thought if we get the right people together, really dedicated to this problem, we could make real progress.
And his proposal pulled together some heavy hitters.
Oh, yeah. McCarthy, Marvin Minsky from Harvard, Nathaniel Rochester from IBM, and Claude Shannon, Mr. Information Theory himself, from Bell Labs. They pitched this summer research project to the Rockefeller Foundation.
And the proposal itself is where the name comes from.
That 1955 proposal, yes. That's the first documented use of artificial intelligence. McCarthy chose it carefully. It sounded neutral, not like automata theory, and crucially, it set it apart from cybernetics and Wiener. He wanted to stake out new territory.
And they started with a premise that was, well, pretty audacious.
Incredibly bold, basically. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. That's a huge claim. If we can understand it, we can build it.
And the workshop goals reflected that ambition language, concepts, problem solving, machines improving themselves.
Goals that are still, central to AI research today. The workshop ran for about 6 to 8 weeks that summer. It brought in other future giants too, like Ray Solomanoff, Oliver Selfridge, Alan Newell, Herbert Simon, Arthur Samuel.
But my understanding is it wasn't like this intense, collaborative research jam session.
Reports suggest it was more like an extended brainstorming session. People came and went, discussions were open, maybe a bit unstructured. Some sources even say the tangible results from the workshop itself were maybe somewhat inconclusive.
So its real importance wasn't about immediate breakthroughs, but something bigger.
Monumental in a different way, yeah. It gave AI legitimacy as its own scientific field. It created a community, a network. It set a research agenda that lasted for decades. It really was like the constitutional convention for AI. It kicked off research into symbolic methods, limited domain systems, all sorts of things.
But that incredible ambition, that belief intelligence could be pinned down and simulated fairly quickly. Maybe that set the bar a little too high.
Oh, absolutely. Thinking you could get human-level AI in maybe 20 years. That optimism, fueled by the core belief and some early successes that felt surprising, it was a powerful motivator. But it also definitely set the stage for disappointment down the road, the AI winters.
Speaking of surprising successes, that burst of optimism right after Dartmouth led to what many call the first real thinking programs.
Yeah, riding that wave, people started building systems that did things only humans were thought capable of. The first big one, widely seen as the first true AI program, was the Logic Theorist. 1956, built by Alan Newell, Herbert Simon, and J.C. Shaw.
And its job was?
To prove theorems from this landmark book of mathematical logic, Whitehead and Russell's Principia Mathematica.
Wow, that's not trivial. How did it work?
It used symbolic processing, representing logic as symbols and heuristic search. Heuristics are like rules of thumb, strategies to guide the search for a proof rather than just trying everything randomly. It was meant to mimic how humans might reason through it.
Did it work?
Amazingly well for the time. It proved a whole bunch of theorems. And famously, it even found a proof for one theorem that was shorter and, well, more elegant than the original one in the book. Imagine that a machine finding a novel proof. It showed machines could do high-level reasoning.
And Logic Theorist is kind of the poster child for early symbolic AI, right?
Exactly. Then Newell and Simon followed up with something even more ambitious around 57-59, the General Problem Solver, or GPS. The idea was to create a system that wasn't just for one thing, like theorems, but could tackle a variety of structured problems. Puzzles, equations, logic, more general.
A general problem solver. That sounds like the Holy Grail almost.
It was hugely ambitious. The key technique they developed was means-ends analysis. You figure out the difference between where you are now and where you want to be, the goal, then find an action, an operator, to reduce that difference. You break the big problem down into smaller steps. It was a pioneering attempt to formalize a general problem-solving strategy.
So these programs, Logic Theorist and GPS, they really seem to confirm the Dartmouth optimism, didn't they?
They really did. They were concrete proof that machines could do more than just crunch numbers. They could manipulate symbols, follow logic, use strategies. Even though they worked in limited, formal, toy domains, their success created this powerful story about AI's potential. And it really cemented that symbolic approach as the main path forward for years. It also gave insights into how humans might solve problems.
But they also showed the cracks, the challenges.
That's definitely. They worked great on problems with clear rules and boundaries, but put them up against the messy, ambiguous real world. They struggled. GPS, especially, showed just how hard generality really is. The methods didn't scale well. It foreshadowed the brittleness of problem systems that work perfectly in their niche but break easily outside it.
And these early programs really marked the start of this fundamental split, this big debate in AI research that lasted for decades.
Yes, almost from the get-go, you had these two competing philosophies about what intelligence is and how to build it.
So, on one side, symbolic AI, also called GFAI, good old-fashioned AI.
That was the dominant camp through the 60s and 70s. The core belief. Thinking is symbol manipulation. Intelligence comes from having a symbolic representation of the world and applying logical rules to those symbols. Like the mind is software running on the brain's hardware.
So you'd program in the knowledge the rules, explicitly.
Pretty much. Build knowledge bases facts, like all men are mortal, Socrates is a man, and then inference engines using logical rules to deduce new facts, like Socrates is mortal. Expert systems in the 80s were the classic example. Newell, Simon, McCarthy, they were the big names here.
And his strengths back then.
Well, it was explainable. You could, in theory, follow the steps it took. And it worked well for formal, rule-based problems, logic, math, games like chess. Philosophically, it lined up with rationalism, the idea that knowledge comes from reason.
Okay, and the other camp, connectionism.
This was inspired by the brain itself, the wetware. The idea here is totally different. Intelligence isn't about explicit rules and symbols, it's an emergent property. It arises from these dense networks of simple, interconnected units, artificial neurons. Intelligence is about learning patterns and rules from data by adjusting the connection strengths between these neurons.
Less about programming rules, more about learning from examples.
Exactly. Think McCulloch and Pitts laying the groundwork for the artificial neuron concept. Then Frank Rosenblatt building the perceptron, an early neural network that could learn to classify patterns by tweaking those connection weights. Philosophically, this is much closer to empiricism knowledge from experience, from the environment.
But early connectionism ran into some big problems.
Huge ones. It was often a black box. You couldn't easily tell why it reached a conclusion. It needed lots of data, which was scarce then. It wasn't great at common sense reasoning. And crucially, those early single-layer perceptrons had real mathematical limits. They couldn't even solve simple problems that weren't linearly separable, like the basic XOR logic problem.
And that limitation is what Minsky and Papert focused on in their book.
Yes, their 1969 book, Perceptrons, mathematically demonstrated these limitations very rigorously. While it focused on single-layer models, the impact was massive. It basically put a deep freeze on connectionist research. Funding dried up.
So that book was a major contributor to connectionism's first sort of winter.
Oh, definitely. It highlighted the limitations of the technology and understanding at that time and really helped cement symbolic AI's dominance for the next decade or so. It's also a classic example of how influential critiques, especially from established figures, can steer a whole research field, maybe even stall promising ideas before they mature.
Which brings us nicely to these difficult cycles in AI, the AI winters.
Right. The term itself, AI winter, apparently didn't pop up until around 1984, but it describes these periods where everything just cools down dramatically. Funding disappears, interest wanes, enthusiasm plummets, usually happens after a wave of hype and promises that don't quite pan out fast enough.
And the first AI winter, roughly 74 to 80. What caused that big chill?
It was a few things coming together. Mostly, it was just the failure to meet those incredibly optimistic predictions made back around the Dartmouth time. People seriously underestimated how hard replicating real-world intelligence actually is. Progress was much slower.
Was there a specific event in the UK that really hurt things?
Yes, the Lighthill Report in 1973. The British government asked Sir James Lighthill to review AI research in the UK, and his report was brutal. It slammed AI for failing on its grandiose objectives and questioned its practical value. Lighthill pointed squarely at the combinatorial explosion problem.
Was that exactly?
It means that methods working okay on small, simple problems just fall apart on complex ones because the number of possibilities grows astronomically, overwhelming the computers of the day. The report basically killed off most AI funding in the UK for a while.
And similar things happened with funding in the US.
Yeah, DARPA, which had been a massive funder, pulled back significantly from basic AI research. They were disappointed with progress on big projects, plus the Mansfield Amendment forced them to focus more on research with direct military applications, less on the blue sky stuff.
So not just one failure, but a mix of unmet expectations, real technical hurdles like combinatorial explosion, and shifting funding priorities.
Exactly. The combinatorial explosion was a fundamental mathematical reality check. Add in earlier setbacks, like the ALPAC report in '66 being critical of machine translation efforts, and Minsky and Paybert's Perceptron's book hitting connectionism hard.
Yeah, it was a perfect storm for a winter.
Sounds like a tough time to be an AI researcher.
Definitely. Confidence dropped, funding vanished, people even started calling their work something else to avoid the AI label, which had become kind of toxic. But, ironically, these winters maybe served a purpose.
They forced the field to face its limits, to set more realistic goals. They probably pushed researchers towards developing more robust practical methods in the long run. It highlights that AI history is cyclical hype, investment, then disappointment and correction. The big lesson was needing sustainable progress based on realistic expectations.
But even with those winters, those challenges, the groundwork laid in those first couple of decades by those pioneers, that foundation clearly still matters today.
Oh, absolutely. The legacy is immense. It's everywhere. Alan Turing, his ideas on computation are the bedrock. The Turing Test still frames how we argue about machine intelligence. Norbert Wiener, he gave us the concepts of systems, feedback, control, fundamental to so much modern AI.
In the Dartmouth crew.
John McCarthy didn't just name the field, he co-founded it. Gave it tools like LISP that were essential for symbolic AI. Marvin Minsky, despite the perceptrons controversy, was key in both early neural nets and later influential ideas like the Society of Mind. Newell and Simon, they pioneered symbolic reasoning, heuristics, problem-solving as symbol manipulation concepts still alive in planning algorithms, search tech today, and Claude Shannon's information theory. It underlies how AI handles data.
It's really striking how much of the core theory, like Turing's universal machine in '36 or Shannon's work in the late '40s, came way before the AI applications we talk about.
It really underscores that long view of science, right? The importance of fundamental research where you might not see the payoff for decades.
And those early debates, symbolic versus connectionist, they haven't really gone away, have they? Just evolved.
Exactly. That old clash isn't so much an either anymore. Now you see a lot of interest in hybrid approaches, like neurosymbolic AI, trying to get the best of both worlds, the learning power of neural nets and the reasoning ability of symbolic systems. And the black box problem, huge issue in early connectionism, still a massive challenge for today's deep learning. It's driving all this research into explainable AI, XAI. So many current challenges trace right back to those early debates and limitations.
And the lessons learned from the hype cycles, the winters.
They're critical. Managing expectations, understanding the limits, the need for steady, long-term research, even when immediate results aren't obvious. Those are lessons paid for during the AI winters. And you also see the huge impact of just personalities. The drive, the vision, the collaborations, and rivalries of that relatively small group of founders really steered the initial course.
So these threads from the past, they're not just history lessons, they're woven into the present and future of AI.
Totally. Understanding where this all came from gives you vital context for what's happening now and helps us think about the road ahead.
So wrapping up this deep dive, the story of AI's birth, it's way more complex and frankly more interesting than just a tech startup story. It's this intricate mix of wartime pressure, individual brilliance, philosophical ideas, big meetings like Dartmouth, ambitious first programs, those fundamental arguments, and then the reality checks, the AI winters.
And those core ideas, universal computation, how to test intelligence, machines learning from data, symbolic reasoning, they are absolutely still driving research. Those old debates about symbols versus connections, they're playing out in new forms, pushing towards hybrids and trying to crack explainability.
It feels like that initial, almost philosophical goal, let's replicate intelligence, ran headlong into the practical limits of the tech and maybe our own understanding back then. And that tension, the vision versus the difficult reality, that still seems to fuel the field.
It really does. The roots are undeniably deep in that WWII era just after. And actually naming artificial intelligence at Dartmouth, defining it as a distinct scientific goal, that was a massive intellectual step, saying, hey, intelligence itself might be something we can study, understand, maybe even engineer, separate from biology.
So as AI keeps building on all this history and just accelerating like crazy, bringing amazing new stuff, but also really complex questions, maybe the most enduring challenge left over from those very first days isn't just how machines can think or what they can do, but that deeper, evolving question. What do we actually mean by intelligence anyway? And how will we really know it when we see it, beyond just ticking boxes on a task list?